We have developed quantum formalism for free fields in the case of scalar fields, vector fields, and now spinor fields. We will then be able to describe the propagation of electrons and muons and also photons. We still have to see how we get antiparticles as excitation of the electron field, that will be a positron, and anti-muon as excitation also of the muon field. Before we get to antiparticles, however, we first need to see the Noether theorem in the framework of field theory. In fact, it turns out that classical field theory will be sufficient, as most of the symmetries of classical fields are also symmetries of quantum fields. It's not always true, but it will be often the case, and for our purpose it will be sufficient to work in the framework of classical field theory. So we will introduce the Noether theorem in the framework of classical fields. Noether's theorem makes a connection between invariance due to symmetries and conservation laws. The connection between invariance and conservation is not a priori straightforward, because these are relatively different concepts. We talk of invariance when the physics is unchanged under a transformation. For instance, we know that in special relativity the laws of physics are unchanged under boost, under rotation, under space-time translation, etc. Conservation, however, relates to a quantity which is unchanged in time. So, for instance, if you take a collision, you have a momentum before the collision and after the collision, which is conserved. So is the energy. These are conserved quantities. And Noether's theorem makes a connection between these conserved quantities and invariance of the physical law, which we also call symmetry. In fact, we should differentiate between continuous symmetries and discrete symmetries. An example of discrete symmetry is parity, when the physical laws of a system are unchanged under mirror transformation, or if you change r into minus r. A continuous symmetry, however, is when you have a parameter which quantifies the amount of the transformation. So, for instance, if you do a translation in space, you can move by a small amount or by a large amount. So you have a continuous parameter quantifying the magnitude of the transformation. You don't have that when you are doing parity, because you just change r into minus r. There is no small amount of parity. In fact, Noether's theorem only applies to continuous transformation, so from now on we disregard discrete transformations. A transformation can induce a change in the field, and this variation of the field can be a function of the field itself, where the function d of phi is somewhat parametrized by lambda. However, to prove Noether's theorem, what we need is infinitesimal transformation, so we will consider a case where lambda is small. In that case, we only keep the linear term in lambda, and we also only consider transformations which are symmetries, that doesn't change the physical laws for the system. So we will label the delta by a small index s, which stands for symmetric transformation. So it's not the general set of possible transformation, it's only those which leave the physics unchanged. And we know that the physics is encoded into the action, so we want to know how the action transformed under this transformation. Again, because it's an infinitesimal transformation, we only keep the term linear in lambda in the change of the action. And we're in classical field theory, so the laws of physics are unchanged if the equation of motion for the field, for the classical fields, are unchanged. And these are given by the stationary action principle. So if the transformation leaves the action stationary, it is a symmetry. If the action is stationary before the transformation, it will remain stationary if we only add a constant as an effect of this transformation. So if lambda delta s is just a constant. How does it translate into the Lagrangian? Well, the Lagrangian transforms also linearly in lambda. And the action is just a space-time integral of the Lagrangian. So we see that for the change in the action to be just a constant, we need the change in lambda to be a covariant derivative of a function of space-time. And indeed, we see that if we substitute del mu f mu in the Lagrangian here, the space-time integral will just bring a constant, and then the change of the action is just a constant, therefore the transformation is just a symmetry. Let's now connect the variation of the Lagrangian with the variation of the field and its derivative, because the Lagrangian is a function of both the field and del mu phi. We will consider that the variation of the derivative is the same thing as taking the derivative of the variation delta of the field phi. We then rearrange the last term using the product rule. We are in classical field theory, and our field obeys the stationary action principle, therefore it also obeys the Euler Lagrange equation. Therefore the first term of the right-hand side cancels with the last term. We also argued that because the transformation is a symmetry, the change of the Lagrangian at most must be a covariant derivative of a function of space-time. We see that we have a derivative of a quantity equal to a derivative of f, and therefore we can rearrange. The quantity between the brackets is called the Noether current. And because its covariant derivative is equal to 0, it's a conserved current. However, it's not just the time derivative of J mu which is equal to 0, it's the entire covariant derivative. Therefore, the time derivative of J mu is not necessarily equal to 0. So it's not a conservation in the sense of a quantity which does not change in time. In fact, we can make the time derivative appear explicitly by using the time-like and space-like components of J, which is just the continuity equation. Note that we use the same letter J for the current, for Noether's current, and for the source which we use to disturb the field in quantum field theory. This is not a coincidence, because often we will use a Noether's current to play the role of a source. Think, for instance, of the interaction between two static sources mediated by a vector field, and which, in the case of a massless field, led to the Coulomb interaction. Well, in that case in particular, we use a source which was a charge density and a current density J. And we know that these densities obey, of course, the continuity equation. So we did all that assuming only one field entering the expression for the Lagrangian. In fact, the Noether theorem generalizes to Lagrangians which are functions of more than one field, and in that case we get a similar expression for the current, except that instead of one field we now have a sum over all individual fields appearing in the Lagrangian. So we mentioned that Noether's current is not really conserved because its time derivative is not equal to 0. But there must be something conserved, because that's what the Noether theorem is all about. There is conservation laws associated to symmetries. So what is conserved, in fact, is the space integral of the time-like component of Noether's current. And that's what we called Noether's charge, which is really conserved in the sense that it's a quantity which does not change in time if the transformation is a symmetry. Indeed, if we take the time derivative of Q, and using the continuity equation as well as the fact that the spatial integral of divergence is 0, we find that Q is indeed a conserved quantity in time.